trap the enolate that's formed with metal iodide. And here now, because it's not bridged, the usual stereochemistry is preferred, usually not always, but usually trans. And for the purposes of your appreciation, let's stick with trans. 84%. Okay? And retrosynthetically, again, if you now, and I keep telling you this, you should not only learn the reactions from left to right, but also from right to left. That is to say, where does the product come from? How can I make it? If you look at this, and anytime you now have a carbonyl compound that has branching at both the alpha and the beta position, you can think of chopping off any of those branches twice, both at the alpha and the beta carbon, because you can potentially introduce them by this reaction here. The major limitation being really the second R group, because it's an enolate carbanion type SN2 reaction, which is subject to the SN2 rules and limitations. So that's cool. Now, what about enolates that we already know in terms of their reactivity to carbonyl functions? And that's back to this. Remember, we learned about the aldol condensation. There, it's an enolate that attacks the carbonyl function. So the question arises, if you have an enone, can we use enolates to also attack alpha-beta unsaturated carbonyls at the beta carbon? And the answer is yes. And so this is nothing else but what one could call the conjugate aldol addition, or the vinylogous aldol reaction, or the aldol attack at the beta carbon rather than the carbonyl carbon. Okay? Completely analogous to all of the reactions we've discussed for attack on this enone. As with all reactions, sometimes seemingly in retrospect trivial variants, whoever discovered it got their name into the reaction. So this was discovered by Arthur Michael. So this is called the Michael addition. So even though it's got a separate name, it's actually just the conjugate version of the aldol reaction. And so what do I mean by this? Here's an example, which I've chosen on top of it just to remind you of the fact that we, in unsymmetrical cases, under catalytic conditions where it's reversible, the thermodynamic enolate is preferred. If you go to low temperature, so that's the enolate that is more highly substituted. So it's this carbanion that you make. Under equilibrating conditions, that is basic alcohol or basic hydroxide. If you wanted to attack at this carbon, you would have to go stepwise. Low temperature LDA, sterically hindered base, will deprotonate at the less hindered, will remove the less hindered hydrogens. But it's very convenient to run these things under catalytic conditions, which are by their nature equilibrating conditions. So if you make the enolate anion here, it will attack at the beta carbon. Again, it will actually more rapidly attack the carbonyl carbon. But again, this is reversible. So when it attacks here, it forms the thermodynamic product because, again, we are retaining the carbonyl group of the recipient here. And so what happens is you get this new compound, but we have a new carbon-carbon bond across here, where this red guy is this guy and the blue guy is that guy. Okay? And red, fitting the color scheme, all nucleophiles are red, so that's the nucleophilic carbon, and all electrophiles are blue, so that's the electrophilic carbon. So I kept it here, so you see where the bond is made. Okay? So mechanistically, in a generic mechanism, enolate anion is formed. It's formed only in equilibrium, you remember, and so it's surrounded by an excess of the enone as well as its own ketone. It can attack all of them. Okay, so the enolate derived from here in equilibrium can attack another carbonyl of its own species. That's reversible, okay? And it will every now and then attack the beta carbon of the enone. Okay? In Michael addition terminology, the nucleophilic component often is referred to as the donor, and this is the acceptor. It's just another way of formulating Coulomb's law. Okay? The electron-rich species attacks the electron-poor species. And you get the new carbon-carbon bond formation here, and you get the enolate formation. And under equilibrating conditions, of course, this immediately gets protonated. Remember, again, first on oxygen to the enol, and then the enol undergoes base-catalyzed enol ketotautomerization to give the product. So again, looking at this from the perspective of how do I use this for retrosynthetic analysis, it's whenever you have a structural unit that has two carbonyls, so it's a dione that's separated by 3 carbons, that is potentially makeable from 2 components, one an aldehyde ketone, the other one an alpha-beta unsaturated carbonyl, by the reverse, well, by the Michael addition reaction. And the beauty of the retrosynthetic analysis is that you can actually cleave not only here, retrosynthetically, the way we made it in this particular generic scheme. Cleaving here makes the enolate component on the left and the alpha-beta unsaturated carbonyl on the right. But you can also cleave here. So if this is an unsymmetrical system, you actually have 2 options of reverse Michael addition. 2 options for the retrosynthetic analysis. If you cleave here, then this 4-atom piece is the enone, and this piece would be the enolate component. And so you should write all this down if this goes through your head to see what it looks like. And if they both look equally good, then you just pick one. But sometimes one version will look much more appealing than another for a variety of reasons. So that gives you additional flexibility. So that's all fine and dandy. And this is actually what occurs at around room temperature. Okay? And these guys just sit there and you can isolate them. Okay? And I'm saying this because some of you may have already recognized, well, this is a dione. We know that carbonyl compounds do all kinds of stuff, particularly under basic conditions. Is it possible that this thing could go on? Well, one of the things it can obviously do and will do for all of these guys in here is that under basic, this is basic ethanol, we get hemiacetal formation of all these species. So the product will be in equilibrium with the hemiacetal because we have basic ethanol here. So ethanol will add, come off, add, come off, add, come off. For carbonyl compounds, alcohol additions are endothermic. So what will be by NMR, you won't be able to see the hemiacetal. Okay? So it will happen on both sides, but you won't be able to see it. But there's another thing that might happen that we actually already executed, in case this looks vaguely familiar. This is a dione. If the dione has positions alpha to the carbonyls that can be deprotonated to make an enolate, then in fact we could do an intramolecular aldol as a follow-up reaction. And this is indeed what happens when you warm up the product that's formed before aqueous workup in this mixture. And that's called the Robinson annulation, named after this character here. So Robert Robinson got the Nobel Prize for this and other chemistry in 1947. The Robinson annulation comes from Latin annulus, ring, so it's a ring formation, is nothing else but an alpha-beta unsaturated carbonyl reacting with a simple carbonyl First by the Michael reaction, which we just discussed, followed by the product, which is a 1,5-diketone, undergoing an intramolecular aldol condensation. And that occurs at higher temperatures, the higher temperatures required to drive the equilibrium all the way to the alpha-beta unsaturated carbonyl. So this is the generic scheme for doing this. You have an alpha-beta unsaturated carbonyl, you have a normal carbonyl. That carbonyl has to have enolizable hydrogens, otherwise all of this is for naught. Okay? If you don't have enolizable, you don't have hydrogens, protons, alpha to the carbonyl, then the carbonyl will be rock stable, won't do anything. Okay? So you have to be able to make the enolate. And conversely, you have to have a Michael acceptor that will undergo the Michael addition of this enolate to the beta carbon of the enone. And for a subsequent intramolecular aldol condensation to occur, you have to have two protons here, because the condensation requires the formation of water that gives you the double bond. Okay? But if these conditions are met, in one step, you can take two components and make a cyclohexenone. Another really powerful transformation. It's in some ways you can view this as a 4 plus 2. It's topologically related to a Diels-Alder, where you take a 4-carbon piece and a 2-carbon piece, and bang, you get a cyclic system, a cyclohexene. Here, you're taking 2 carbonyl compounds and you get a cyclohexenone. Okay? By a totally different mechanism, of course, but it's a powerful disconnection, again, in terms of unraveling a 6-membered ring. So here's the example that we started off with. Let's finish it off to the intramolecular aldol. So again, we're starting with methyl cyclopentanone and 3-butenone. That's the reaction we saw earlier. In this particular example, that gives 86% of the Robinson product. They actually use sodium methoxide and ethanol at low temperatures. At low temperatures, you only get the Michael addition, meaning you make the enolate, the thermodynamic enolate, the most substituted enolate. The nucleophilic carbon, red, adds to the beta carbon here to give you this compound. So here's the new carbon-carbon bond that's formed between this and that. And -10, it's stable. But if you warm this up, under the basic conditions, you get deprotonation here to the enolate over here that attacks here to make the aldol adduct. Actually, in this case, they warmed it up just a little bit to be able to even to isolate and observe the aldol intermediate. But in most cases, we don't care. We just heat it up sufficiently that dehydration occurs to make the corresponding cyclohexenones. Remember, the rules for intramolecular aldols, you've got to make 5 or 6 membered rings. Everything else is too strained. Okay? And in particular, 5 and 6 membered rings that have no other steric hindrance associated with them. I'm saying this because, as you notice, in order to get from here to product, I'm making the enolate around here. In other words, I'm deprotonating this carbon. But in principle, you could also deprotonate here. But remember, this now would have to attack here. That's a 4-membered ring aldol product. That's too strained. Alternatively, you could use this carbonyl as a source of the enolate. And that is an unsymmetrical carbonyl. So again, it has two sides. This one here won't go because there's no proton there. Okay? So that's completely substituted. So we only have to consider this one. And going from here to this carbonyl over here, notice that would give a bridge. Okay? That would put this carbon up onto a bridge because you're making a bond between here and here. And that is also too strained. It doesn't lead to a 6-membered ring product. So it's a simple rule. 6 or 5 membered rings, typically 6 membered rings are best to make the corresponding cyclohexenone. And notice that this can be done all in one pot without isolating anything. You just take these two guys, boil them up with sodium methoxide and ethanol, and you get a high yield of this corresponding cyclohexenone. Okay. Here's an intermolecular case, carefully chosen to avoid all kinds of possible side reactions. So this Michael acceptor, for example, has no alpha acidic hydrogens to cause trouble. Okay? And this one is symmetrical. Okay? Otherwise, that would also cause trouble. Okay? So you may have already guessed. A lot of things are possible. And if they are possible and there are hydrogens there that will do it, indeed, you get a horrendous mess in these reactions. So sometimes you have to carefully choose what you are starting off with. This one, with sodium methoxide and methanol, makes the enolate here. That's the only enolate you can make. So this is going to be the Michael donor, and it will add by Michael addition. And then you get an intramolecular aldol involving the other methyl group of the acetone, and out comes this. Okay, so looking at this retrosynthetically again, this is the double bond that is made in the intramolecular aldol reaction. So here, this used to be a carbonyl. This carbonyl here. This carbon, well, these two carbons used to be this double bond. They get destroyed by the Michael addition of the enolate here that attacks here, and this carbonyl gets destroyed by the other side of acetone, using its hydrogens to do the intramolecular aldol condensation. Again, this means that cyclohexenones can be split by the retro-Robinson annulation into two components. One is an enone, the other one is a ketone. Okay. So there's a movie for that. Robinson. Oops. That's the example up there. So we have the enolate attacking in the Michael. You get the new enolate. The enolate is protonated, first to the enol, and then proton shift to the ketone, and then you get the intramolecular aldol reaction. First an enolate. The enolate attacks the carbonyl. Get the alkoxide here. That's protonated. That's the aldol adduct, which we typically don't isolate because we boil this up such that hydroxide is now capable of deprotonating again over here. Now watch this. Whoa, this hydrogen jumps through here. And the enolate then kicks out hydroxide to make the enone. Now, I grant you, looking at your glassy-eyed expressions, this is difficult. Not intellectually difficult. It's just a visual part of it. Okay? And that's something that organic chemists, and you will pick up, already have picked up a lot of expertise in this. The capability of seeing a molecule on a flat sheet of paper in 3 dimensions. The capability of seeing these disconnections, the way, like in a puzzle, the pieces fit together by just looking at the structure, recognizing patterns, and so on. You'll get better and better at this. It's an art. And my wife is an artist. And when we first met and I showed her what I did for a living, she was totally flabbergasted. Okay? She thought it was incredible. That the view that you develop in this exercise is that of an artist view. So there are very many reasons why this is actually a useful exercise, just apart from the fact that you learn something about molecules, how to make them, and how this all applies to natural systems. Let's have a break. Okay, so that brings us to yet a new functional group, which is really the old carbonyl just modified. And the modification is quite profound because we are taking away, in an aldehyde this would be a proton, in a ketone this would be another alkyl group, we're taking away one side of the carbonyl and we're replacing it by OH. OH generates what is called carboxylic acids. The pKa's are sufficiently low that they, as human experience, act as acids. In other words, we feel them when you drop them on your skin, it starts stinging. So that's why they're called carboxylic acids. They nevertheless react very much like carbonyl compounds, except their reactivity is attenuated. And the reason for that is that this electron pair can donate into this carbon by resonance. And therefore, the positive charge on this carbon is diminished. And overall, thermodynamically, the system is more stable than an aldehyde or ketone. Carboxylic acids are abundant in nature. They are the last oxidation step of organic compounds before they turn into carbon dioxide, combustion, or metabolism in your body. So carboxylic acids are all over the place, in your body, all over nature, and so forth. Any further oxidation kills them to make carbon dioxide. Okay? And so they are quite, as I said, much more stable, much less reactive than carbonyl compounds, but they're sufficiently reactive that there's very rich chemistry. And part of that chemistry will be to replace OH by other leaving groups, not unlike alcohols. So in many respects, you can also view these not as modified ketones in aldehydes, but as modified alcohols, where the R group in an alcohol has been replaced by an acyl group. Okay? And that focuses on the reactivity of the OH rather than that of the carbonyl. So the two influence each other to give rise to new properties by modifying the properties of the individual components. And so one thing that happens is, of course, this guy is acidic. Of course, the lone pairs impart basicity, and this carbon is still electrophilic, although not as electrophilic as in aldehydes and ketones. So if you, and this functional group is called the carboxy group, and it's typically written COOH, or if you don't like that because this looks like hydrogen peroxide or hydroperoxide, CO2H. In fact, that's probably a better way because it's also shorter. Okay? If you're confused by this, write it out. Okay? CO double bond OH. Now, here is the answer to the questions of many of you. When will we get the entire hierarchy of precedences and naming of all the functional groups? And here it is. Okay? And this looks like a mouthful, which I intensely dislike. I don't want you to memorize ad infinitum. That's really boring. Okay? So what I'm going to ask you to do is lump all of these guys on the left together. The bottom line is carboxylic acids are king. They are tops. Okay? Anything that has a carboxylic acid function in it, regardless what the rest of the spinach looks like, it's a carboxylic acid that's substituted. Okay? So all other functions have lesser priority. In other